Good morning. So today I am going to discuss on the topic of biased and unbiased estimators. Okay, so we are going to see what do we mean by biased estimators and what do we mean by unbiased estimator. Okay, so consider an estimator theta hat which is some function of the observations. Okay, so what can we say about this? That theta hat is a random variable because it's a function of random observations. Now suppose theta lies in the range A to B, then what do we mean by unbiased estimation or unbiased estimator? So an estimator is unbiased if following condition holds, that is average value of theta hat, average value of the estimator equals the unknown value, unknown parameter for all theta in the range A to B. What does that mean? That means that suppose A equals 1, B equals 2, theta equals 1.9. So then our estimator theta hat is unbiased if average value of theta hat equals theta equals 1.9. Okay, now let's take an example. So let's take an example to explain the above points. Let's take an example of an unbiased estimator. Okay, so consider the problem of DC level estimation A plus Wn for n equals 1 to n minus 1. Okay, so consider the following points. A has to be estimated, that is theta equals A. Point number 2, Wn, that is the noise, is white Gaussian noise with distributed as normal and variance sigma square. Thirdly, the value of A can be any value, okay, which I'm writing it like this. Now consider the following estimator. A hat equals, okay, that is the average of the observation. So we need to know, remember we are going to discuss about the biased and unbiased property of the estimator. So, and each estimator is a random variable, so we need to know what's the average value of the estimator A hat. Okay, so let's find it out. So average value of A hat equals average value of the following expression. Alright, which we can write as like this. How we can write it like this? Because as the expectation operator is linear, so we can bring the expectation operator inside the summation term. Then we can write the above expression as like this as A. Okay, so the average value of the estimator A hat equals A. So what does that mean? So average value of A hat equals A. That means A hat this estimator is an biased estimator. Why? Because the average value of A hat is A itself. Okay. So now let's plot the PDF of this estimator. So its mean value will be A and it will have some variance that we will later discuss. Okay. So I'm drawing the PDF of A hat. Its mean value is A. Okay. So this is an See, the mean value of probability of A hat is A. That means A hat is an unbiased estimator. Okay. So now consider a general estimator. Consider an estimator theta hat, which is some function of the following observations. Okay. So we can write average value of theta hat as integral the estimator function parameterized by the estimator function multiplied with the probability density function of the observations parameterized by the unknown parameter theta integral over all the observations okay. And if this estimator is unbiased, then this value should be equals to theta for all values of theta. Okay, so this was a general expression for a general estimator. So it is a condition for an unbiased estimator. Good. So now let's take another example. Okay, example 2. Let's take an example of a biased estimator. Remember, earlier we had discussed about unbiased estimator. Now we are going to discuss an example for a biased estimator. So let's take the same data model. Now, point number 1 is our unknown is A, and let's say the estimator A, suppose I say it A tilde, suppose I call it A tilde, the estimator as 1 over 2n summation of xn. So this is our new estimator. Earlier it was A hat, so now it is A tilde. Again we need to find out the average value of this estimator. Okay, so we repeat the above procedure again. We bring the expectation operator inside. This gives average value of A tilde equals A by 2, which is equals to A if A is 0, otherwise not equals to A if A is not equals to 0. Okay, so we can say that A tilde is a biased estimator. Why? Because average value of A tilde is not equal to A if A is non-zero. So earlier we had said that an estimator is unbiased if it is equals to the unknown value A for all values of A. But here this is not true if A is not equals to 0. Okay, it's true only for A equals to 0. But it should be true for all the values of A. Therefore, we can say A tilde is a biased estimator. Okay. So now let's study the properties of unbiased estimator. First property, let's consider a large number of estimators. A large number of estimators, theta 1 hat, theta 2 hat, theta n hat. So these are the different estimator of the same parameter theta. So now suppose we average all these estimators. Let's consider theta hat equals average of all these estimators. Then the question is whether we get a better estimator or not. Okay, so if we average a large number of estimator, whether we get a better estimator or not. So assume that each estimator theta I are unbiased estimators. Okay, so we can say if we find the average value of theta hat, that is average value of 1 over n theta I, then what will be this equals to theta? Okay, theta, because theta I are unbiased. That is average value of theta hat equals theta. Then what's the variance of this estimator? Variance of theta hat is given by this expression. Okay, which we can write as variance of theta I hat over n. If they are all same, we can write it like this. Okay, so we observe that as we take a large number of estimators, n approaches to infinity, theta hat approaches to theta, and variance of theta hat approaches 0. That means we get a better estimator. But this is true for unbiased estimators. So Let's see what happens if we have biased estimators, if we use biased estimators. Okay. However, if theta I had are biased, that is, average value of theta I hat is a sum of two components, that is theta plus the bias term plus the bias term. So now if we find out the average value of the estimator, then what will be this equals to? Nothing but theta plus b of theta. So what does that mean? Okay, what does this equation say? So this means that even if n is large, the bias will remain. The bias will remain. So bias theta can be written as average value of theta hat minus theta. So now I am going to plot the PDF here. For the above estimator, this is for the unbiased case. As n increases, and this PDF is for the biased case. So we see that the mean for the biased case is away from the actual value. So this is the bias. Okay. So we see that even if we increase the value of n, the bias remains as is shown in this PDF. So that's all for the today's lecture. Thank you very much.